So anyway, just so that it's just for the completeness sake, for the YouTube part, I'm going to start over briefly and saying that I will talk about this measurement-dependent locality and later on a little bit also about something I call limited detection locality. At this point, none of these two concepts have to make sense. If at the end of the talk they still don't, then I didn't do my job. So what I want to do here is very briefly introduce the concept of the device-independent setup, which of course most people here in the audience know. Actually, everybody will know, otherwise you wouldn't be at this particular workshop. But so that we all speak the same language, I will look at the particular case where we have a quantum state rho which is distributed to two parties. All the results that I will present are kind of trivially generalized to more parties, so this is not a requirement, but let's first look at two for now. These two parties each get an input. Based on this input, they perform a certain measurements given by these POVMs here, and given by that, they get a certain outcome, and they have a probability of these outcomes given the inputs, which is given by the trace rule that we all know. And now, of course, in a device-independent setup, we want to get rid of most of that. Specifically, we want to get rid of rho. We want to get rid of the POVMs. We just want to consider there's inputs coming, there's outputs going, and we're going to have some output correlation PAB given xy. What I'm going to consider here is where we have an adversary in the middle that has control over some lambda. And based on this lambda, that adversary is going to distribute some form of correlations to our two parties here. And this is going to be what is going to be observed after you average out this lambda here. Note at this point, I have not yet made the assumption of locality, even though I put a lambda in the middle. That's just based on this lambda, there's going to be some box here. This lambda could be the quantum state, for example. So what assumptions are usually made in a device-independent scenario? So the first assumption I think that we all usually agree on is that we make the assumption of no signaling. So there's no signal somehow communicating the input on one side to the output on the other side. So the output on this side does not directly depend on the input here. And of course, the same is true for the other way, but so not to clutter the figure, we only have one of the two here. That's the assumption of no signaling. The second one that is usually made, I would say, is measurement independence. So that one is the fact that whatever our adversary is doing here in the middle, it cannot depend on the measurements, on the inputs kind of that are coming. So the inputs and this knowledge here in the middle that the adversary has, they are uncorrelated. And actually, that part is already kind of hidden in the fact that I did not put a conditioning on xy in this P of lambda here. Now, let's say these are the two assumptions that are always going to be made, I think, in most device-independent scenarios, except for a few. One thing that we could now do is, OK, let's say we want to check that our outputs here are somehow indeterministic, that there's some randomness. We already heard about randomness extraction earlier, so let's consider that case. So let's also make the assumption that the outputs are somewhat deterministic. So our outputs only depend on the lambda as well as the corresponding inputs over here. And I think for everybody here, it's pretty clear that this is the same as if I made the assumption that there's outcome independency. In other words, it's the same as making the assumption that we're local. So this is a non-trivial result, of course, but it's a well-known result, so I'm not going to go into details of that. So in the end, what it comes down to, if you make these three assumptions here, no signaling, measurement independence, and determinism, you find that you get all possible local correlations. So all correlations where the outcome here, the probability of the outcome here only depends on the input on that side and whatever was distributed from the middle. So now we arrived at locality. What I am most interested in is that this is a very strong thing because, for example, now when you're non-local, when you have a correlation PABXY that cannot be done in this way, then you automatically have some randomness in the output. I'm not saying it's quantified at this point. I'm not saying it's unknown to the adversary. I'm just saying that your outcome definitely was not deterministic because the determinism here was an assumption. But what I want to do is actually not particularly look at this now. What I want to do is I want to look at this. Because this measurement independence assumption is kind of annoying. If you look at it from a philosophical point of view, where somebody wants to say, oh, our universe is random, it's non-deterministic, then I'm kind of assuming non-determinism here originally to end up with non-determinism later from Bell inequalities, which is not very satisfying. If you look at it from an adversarial point of view, if you're doing quantum cryptography or something, it's even worse, because for some reason you're assuming that the random number generators that you're using to feed your quantum cryptographic device, that they are somehow not influenced by the adversary at all. So for some reason you have a very secure device at home. Okay, yeah, that's fine. You can maybe assume that, but if you don't have to, then why would we? Problem is we have to a little bit. Because if I just get rid of this assumption totally, if I just say you can, this adversary here in the middle can totally influence the inputs on the both sides, then I'm actually quite in trouble because there's no way to protect against anything now. Now, anything that you can do in quantum mechanics, you can do with something like this. So you can easily get deterministic outcomes if you know the lambda, and it's going to look like any quantum distribution that you like. So we have to make some assumption, some form of assumption here. And the assumption that I propose in this case is that we make the assumption that these inputs here, the correlation between the inputs and this lambda, has a lower and an upper bound in terms of probabilities. Now, this may look familiar to already several of you. For example, if you make an assumption on the min entropy, that is what it looks like. Santavasirani looks kind of like this, but it goes a little bit further because here I'm still assuming some form of IID. But this is the type of assumptions that come up again and again. So this is the one that I want to study here. And if you notice, I rewrote this part here now into something which actually takes care of the distribution of the inputs. So I'm no longer conditioning on the inputs. I'm looking at the distribution as well, which seems reasonable the moment you want to consider something like this. And this is what I will call measurement-dependent locality. So that is the first concept in the title. So I'm hoping that I managed to clarify that one already. So if you have determinism, so you have local distributions here, you still have your no signaling, and you have this assumption here in addition, then I will call that measurement-dependent local distributions. And since I still have the determinism assumption here, measurement-dependent non-locality still guarantees some form of randomness, where the guarantee is, of course, to take with a grain of salt at this point. And this was all done in a paper that I published last year. Honestly, the only reason I'm putting this here is because since this will be on YouTube, it might be useful for somebody to be able to look up the paper. OK, and the study of this, which is in this paper, relies on mainly one technical result that I very briefly want to show. It's going to be the only technical slide of this presentation. And before I can actually get to that, I need to explain what a polytope is, even though a lot of people here, again, are going to know that. A polytope is a convex structure which is fully described either by giving you a finite set of vertices, so I give you a finite number of points, or I give you a finite number of linear inequalities. Think of a cube, for example. If I give you the vertices of the cube and I tell you take all convex mixtures of these vertices, you have the full cube, you're done. Or I can give you the inequalities which describe each side of the cube and then just say it's everything that's inside these inequalities that respects all of them. Then you also get the full polytope back. And these things are very nice because it's kind of easy to optimize things over them. They have a rather efficient characterization in general because as soon as I give you the vertices, you now know everything that you need to know. And if we now look at these distributions which are of this type here, so they have here something, and then they are combined like in a sum like this. Then we have a little theorem, which is in the appendix of the paper in case you're looking for it, that if these distributions here were chosen from some polytope originally, these distributions here were chosen from some polytope originally, then what you get out at the end is again a polytope. And not only that, I can even give you the vertices immediately if you give me the vertices of these two. So you give me the vertices of this one and of this one, I give you the whole vertices of these ones. So I can give you kind of immediately the full characterization of this set. Specifically, this means that these measurement-dependent local correlations that I just showed earlier, they form a polytope. Because with this particular type of assumption, if you see it's linear assumptions, that makes this a polytope. And this local stuff here, that is well known to be a polytope. That's where all the Bell inequalities are coming from. OK, so basically, this set as well is going to be fully characterized by linear Bell-like inequalities. So that is the first thing that I want to really note here, because that is what makes a lot of results possible. This is what the technical part that all of this is based on. Now let's get to the interesting part. The interesting part is going to be given later on by this particular inequality here. It's not too important what this inequality is. I just want to show it because it's simple enough to actually put on the slide. So I might as well put it. So this inequality here depends on the L and H parameter that you have to set here originally. And given that all of these correlations here satisfy that if you compute this value here, it's going to be smaller than 0. And the fun fact is that you can find a quantum violation of this for all L that are strictly larger than 0 and for all H. So literally, you make this assumption here as weak as you like. Earlier, I said that we had full measurement independence, which was a very strong assumption. Now you can make this assumption as weak as you like, and you're going to still be able to find a quantum violation. So quantum mechanics is measurement-dependent non-local with arbitrary little pre-existing randomness, or if you give your adversary, I'm going to say, arbitrary lots of control over your random number generator, where arbitrary much means that there is this lower bound L here that you can set. This is the assumption that you have to make. Even better,
for all H less than 1 or for all H?
For all H, because the quantum strategy that you're going to choose is going to set these 3 values to 0. And this one's strictly positive. Actually, for those of you that recognize this maybe, this is Hardy's paradox. Hardy's paradox managed to set all 3 of these to 0 and have this one strictly positive. And for those that know a little bit background of Hardy's paradox, they already then now know the next thing that I'm going to say. Because Hardy's paradox can be violated by any pure partially entangled 2-qubit state. So you don't need anything complicated. You don't need 5 qubits or 7 parties or 20 inputs or whatever to show this measurement to show that quantum mechanics cannot be reproduced in any way as long as you have this L non-zero. You can literally take any partially entangled state, as long as it's pure, and then you just need to find the right measurements to do it. But this can be done. Particularly, for example, you can take this nice state. This has a sufficiently large violation. Why do I write it here? Well, first of all, it's pretty. It has the golden ratios as its coefficient, so I like it. It was the first one that I found back when I didn't realize that this was actually Hardy's paradox simply. This was the one that I usually turned up. And this is also, I want to say, why do I insist so much on this 2-qubit thing? It's experimentally feasible to do such a thing. Now, the part that's not experimentally feasible is the pure part. But if you're not fully pure, what this means is that you're not going to be able to exclude all L, but still a lot of them. The closer you are to the state. This is what you can do there. And it's not only experimentally feasible, it's experimentally has been done. So that's a paper that we published this year as well, where this state here was implemented with fidelity of 0.99. So we got very far already on this. So this is work that can be done. Now, why is this so interesting? Well, most of the work that you do, if you look at works in randomness amplification or similar, they usually require rather complicated states, many parties or something like this. Here, you take any partially 2-qubit state that you happen to be able to do in the lab, and you can work with it, if you can do the measurements.
And of course, you denote it AU because it's a chemical symbol for gold.
Yes, exactly. Because I like the golden ratio in here, so I called it the golden state originally. This was my code name for this state for a long time. OK. Now, at this point, when we're here, what some of you might be saying is, well, great, you can protect us from local adversaries. We didn't care about those. Because if we can do quantum mechanics, then we assume that our adversary can do quantum mechanics as well. So what can we do in this regard? Well, then how about we talk about measurement-dependent non-signaling. So let's go back to this slide here, where I earlier showed measurement-dependent locality. And let's get rid of this determinism assumption. Let's no longer look at local distributions. Let's now just assume that whatever our adversary does here is still limited by no signaling, so even by more than quantum. It's a post-quantum adversary. Somebody can do stuff that is beyond quantum mechanics. And I'm going to call that measurement-dependent non-signaling. And the nice thing is the technical result that I showed earlier, the polytope result, didn't care what the exact structure here was. It just needed the polytope. The no-signaling correlations are such a polytope, so this still forms a polytope. So using this now, you can try to use the correlations that you can find in this polytope here and see, like optimize over these given certain constraints to find, for example, what is the guessing probability of the output A here. Now, I'm not saying that this is something easy to do, which is why I haven't done it yet. But the technical background is there. Now the work is still required, and this is ongoing work where since this is a workshop, I want to point this out. This is something where I would be interested in collaborations with people that have more expertise in the area of guessing probabilities and similar type. OK, are there any questions here so far up to this point? If yes? Yes. No, so your adversary is allowed for every lambda that can come here to choose the probability of these settings, but you have to respect these two bounds. So, but the adversary, for every lambda here, so let's say, the way you should think about this, I think, your adversary is going to distribute boxes to you. So these boxes here, these non-singling boxes, maybe given by a quantum state, maybe given by something else. Okay? And he's going to give you different boxes, which is going to be encoded in this variable lambda. So this variable lambda is what he records which box he just gave you. And depending on the box he gave you, he might say, oh, it's very beneficial for me if these inputs here, like the input 0, 0, for example, are happening right now. So I want to bias towards having the input 0, 0 when I give you this box. And that is what we're allowing him to do here. So based on what box he gave you, he can influence your inputs to a certain way. Your random number generator that you use in the lab, that you use for your QKD system, he is allowed to influence that. But within this limitation here. OK? OK, so this was the first part of the title. The title had a second part. The title had a part called limited detection locality. Let's first talk about what I mean by limited detection efficiency. I'm going to be the first to admit that this is not yet the best name. So if somebody can come up with a better name, that's going to be great. But for now, let's go back to this quantum scenario where we did measurements over here. If you ask any experimentalist what is the most annoying thing that is going to happen in the lab, well, it's going to be the fact that no matter how well you do your straight preparation and you perfectly align your beam splitters and whatever you use to do your measurements, you're still going to have some form of losses. Your detectors are not going to click even though they're supposed to. You have detector inefficiencies and all that kind of stuff. So overall, you have some non-detection events where the particles that you created just got lost, where the detector didn't click even though the particle arrived, stuff like this. And so you have these non-detection events, which I'm going to denote by this particular symbol here. You're going to have them on both sides. I'm always going to just write down for one side for space purposes. And there's two things you can do here. Either you make very strong assumptions, like saying, oh, yeah, but my detectors are not controlled by my adversary. My adversary is not using that at all. That's fine. And then you can keep your beautiful, nice correlations that you got by doing lots of work on the state preparation and lots of work on the measurements. But yeah, you pay for that by making these strong assumptions that in a device-independent scenario, and especially at a workshop called trustworthy quantum information, we really don't want to do. So then you're left with the other one, which is usually that people make no assumptions. They say, oh, yeah, my detectors are fully controlled by my adversary. Every loss is basically used by the adversary. We're being very, very paranoid here. And that leads to your correlations. I call that weakened because you add a lot of noise by doing so. What I want to propose here is the idea of going to a middle ground. Now, this is no longer fully the usual device-independent scenario, moving slightly away from that now. And the middle ground that I want to say is that, yes, your adversary has control over your losses. Your adversaries may be able to influence the detector by playing with the power supply to your lab or something like this, but not perfect control. So your adversary cannot decide to guaranteed lose a particle or to guaranteed detect a particle. Now, the upper bound is a little bit easier to believe, I guess. I think most people wouldn't believe that you can, with guarantee, detect a photon, with guarantee, make a detector click, even though there are certain detector blinding attacks that do just that. But for now, I want to offer this possible additional assumption, or at least propose them as something to be worth considering. Because in certain in certain scenarios, this no assumption case is just not going to work. If there's no assumption case, for example, when you want to play a CHSH game with a maximally entangled state, you need 82.8% efficiency to have anything. And I can send you to several people that experimentalists that are not going to be very happy if you tell them that, please, give me 83% efficiency in your experiment. It's not easy to do. So in the cases where you can't do that, you don't want to immediately just make the assumption that your losses are completely non-due to the adversary, but go to this middle ground here. And this is what I call limited detection efficiency. Yes?
Bracket is not statistical. It's for each particle individually.
Yes, so that's, okay, so here's one thing, of course. Yes, I'm still making an IID assumption here. Yes, I'm still making the assumption that you have some access to these probabilities here. So yes, in this case, the probability of having a non-detection based on the input and based on this hidden thing that happened in the middle is upper and lower bounded. That's
the point is this cannot be measured.
No, this cannot be measured. This is an assumption that you're making. Just as before the MDL one, you also couldn't measure. This is really meant for the case. Obviously, if you can do this, if you can make no assumptions, go ahead. But in the cases where you can't, here's, I think, a good proposal to consider. So now let's go back to, for example, this case where we had this no signaling, measurement independence, we had determinism, we had this whole shebang here that I presented earlier already. So we're now back to having measurement independence for now. And let's make this additional assumption here, that the non-detection events that you get, so you have no losses, but the non-detection events that you get are upper and lower bounded even for your adversary. And this is what I call limited detection locality. And there's a paper coming out on this soon, so it's basically written up, which is a study of this particular case. It forms, again, a polytope. As you can see, I quite enjoy polytopes. So there's a lot of nice results to be derived directly from that. The only one I want to speak about today is that actually you can combine this limited detection and the measurement dependence very straightforwardly. What I'm saying is if you make these assumptions, so now I'm adding measurement dependence as well. So now you have no signaling, you have measurement dependence given by this L and H. You still have your determinism, so we're still in the local scenario. And you have this eta min and eta max, so you have these two additional parameters here for your limited detection efficiency. And what you actually can do is you can skip this and just put it in here. And the reason why you can do that is because the way an adversary would use non-detection events is to avoid inputs that they don't like. So it's something. So basically, they're choosing the inputs. They're influencing the inputs that they accept, that they don't accept. Now, what do I mean specifically by this? It's not exactly the same. What I'm saying is, if you have measurement-dependent locality with this L and H, and you have limited detection locality with this eta min and eta max, and you have a correlation that you can reproduce using these resources, then an adversary could reproduce using these resources, then that same adversary could also reproduce them using just the measurement dependence with an adjusted L and an adjusted H. So what this kind of means is, if it's the backwards way that's interesting, if you're out of this set here, if you have correlations that cannot be reproduced in this way, then they can also not be reproduced in this way. That's the way to look at this. It's not a full equivalence. But what is really nice about this, I think, is that you can now immediately take all the results from a measurement-dependent locality that were published last year, and they kind of directly apply to this. If you want to do it with measurement independence and you just want to look at detector efficiencies, you just set this L and this H to be equal to the uniform distribution, and now your university has no power anymore over the inputs directly, and then you get this out as well. What is nice here is earlier I said that we are measurement-dependent, non-local in quantum mechanics using any partially entangled pure 2-qubit state, as long as this lower bound is non-zero. Well, this lower bound is still non-zero now as long as your eta min is non-zero. So again, this assumption can be made arbitrarily weak. So the eta max you can set to 1. Don't care about that. The eta min has to be strictly positive. And if you make this assumption, then actually independent of your detection efficiency, we can make correlations in quantum mechanics that cannot be reproduced by this. So you make a very weak assumption, which is that this eta min is non-zero. That's the only assumption you make. And now I do no longer care about 82.8% efficiency or whatever efficiency. You can have 0.1% efficiency for all I care. Because with this analysis, if you do the right correlations with the right measurements, they could not have been reproduced by this. So this allows you suddenly, instead of having this like very high efficiencies that are necessary, they are no longer necessary. Like I didn't make any assumption on the average detection efficiency here at all. You can make those assumptions as well, and they're going to help you more. But you don't need them anymore. But of course, it comes at the price. It comes at the price of making this assumption. All right. So with this, I would like to actually conclude. I'll rather get to the outlook here. So maybe a conclusion I briefly do by words. What I wanted to introduce were these two concepts of measurement dependence and of limited detection efficiency, which I think are two interesting concepts. One is a weakening of the usual assumptions. One is a strengthening of the usual assumptions. But both work together really nicely. Both work in helping an adversary to counterfeit correlations in such a way that it is beneficial to them. And the outlook that we have, that I would have here is that so a more extended study of this measurement-dependent locality, so more inputs, more parties, what inequalities come, what states are interesting, what can we actually do in this regard. That is actually something that I'm currently working on and that I will be writing a paper on rather soon. More interesting, already I think Valerio pointed this out this morning, the non-IID case. For what I did just now, I assume that you somehow get access to the full correlations to the PAB given XY. I did not make any, I did not allow for the fact of, you have repeated measurements and maybe the second scenario depends on what happened in the first one or whatever. I'm making an IID assumption here. And that is, of course, an assumption that if you can get rid of it, it would be nice. But that is also probably the hardest thing to deal with, I think, in most fields that we are working in today. So if somebody has a good idea how to work with that, that would be very helpful to know. I would like to see if this can be used in protocols. So for example, if you look at randomness amplification, 2 years back when the paper by Rodrigo Gallego and co-authors with Tony Yasin and so on came out, where they did randomness amplification, they used 5 parties, a perfect state, stuff like that. I'm wondering if using this polytope now, you could maybe do this in the bipartite scenario already. Now, I don't know if this is doable. I have not studied this yet, but this is something that would be interesting. So if there's experts in this area here, then I would also be interested in talking to you. And finally, the use of this measurement dependent on signaling, which goes together with here, that I have not used at all. I know of this. I've known of this since I published the paper, even though I didn't even put it in the paper because I didn't have a direct use of it. I have not used this yet. So that is also something that I think can be exploited still. And in the limited detection locality thing, this still needs to be explored independently of measurement dependence to see if this is maybe an assumption that experimentalists might be interested in that is worth to consider in actual, I don't know, QKD protocols or something similar. And that I probably will either get into myself or leave up to any experts in the area. Thank you for your attention. Yes? Yes.
Did I understand correctly? You're saying that will violate the non-zero lower bound?
Yes. Well, actually, any partially entangled 2-qubit state is going to do it. This is a partially entangled 2-qubit state, so yes, it will. You have to do the right measurements. So what this is going to do, if you do the right measurements on this state, you're going to have a 0, a 0, a 0, and a non-zero value here.
So do you have to know, when you say the right measurement,
No, that's independent of that. That's the nice thing. If you do the right measurements here, you really put these 3 values here to 0. So everything that's negative here is 0, and what you're left is with something positive, right? So you're going to violate this inequality immediately because you're going to get something strictly larger than 0 here. So it's independent of the values L and H what the optimal measurements are. Yes?
Yeah. So to follow up on that, it seems like then if you have any noise whatsoever, then you might, like you think depends on 0.
So what's going to happen if you have non-zero noise and you have imperfect measurements? You're going to give some contributions here, right? So you bound L and H. That is exactly what you're doing. So basically, in the experiment that was done here, we found so if you set H equal to 1, we found that you can bound the L to be 0.073, I think, was the value. So which is far away from 0.25, which is the measurement independence assumption. That's setting it to 0.25.
All the speakers, but